A very long time ago, a quiet corner of our galaxy held a vast, cold cloud. It was an immense expanse of drifting gas, fine dust. This was our solar nebula, a cosmic nursery waiting for a spark. About 4.6 billion years ago, something disturbed its peaceful existence. Perhaps the shockwave from a nearby dying star, a supernova, pushed into the cloud. This gentle nudge was enough to set things in motion. Gravity, the silent architect of the cosmos, began to pull the material of this great cloud inward. The cloud started to collapse upon itself, a slow and majestic fall toward a common center. As the cloud contracted, it began to spin, like water swirling down a drain. The rotation increased as the cloud shrank, a fundamental law of physics playing out on a galactic scale. The vast majority of the gas and dust spiraled into the very heart of the collapsing cloud. The pressure and temperature at this core began to climb to unimaginable levels. Atoms were crushed together with such force that they ignited in a brilliant flash of nuclear fusion. In that moment, a star was born. Our sun flickered into life, bathing the surrounding space in its newfound light, bathing the surrounding space in its newfound warmth. Around the infant sun, the remaining material did not fall into the center. Instead, the force of the spin flattened it out into a wide, spinning plate of gas and dust. This was the protoplanetary disk, a cosmic potter's wheel from which the planets would be sculpted. It was a chaotic and dynamic environment, filled with the raw ingredients for worlds. It stretched for billions of kilometers, a thin, dusty ring encircling its brilliant parent star. From this swirling disk of leftovers, the entire solar system, with all its wonder and complexity, was about to emerge. Everything we know, from the ground beneath our feet to the farthest frozen worlds, began right here. Imagine standing on a precipice, watching this cosmic event unfold. You would see a breathtaking spectacle of light and shadow, a swirling vortex of creation. The young sun would glow with a fierce, youthful energy, and the disk around it would be a dark silhouette against the backdrop of distant stars. This disk was not uniform. It was a place of texture and temperature gradients, a place where the story of the planets was already being written in dust and ice. Within the swirling protoplanetary disk, the process of building planets began. It was a slow, patient process of cosmic construction. At first, there were only microscopic grains of dust, smaller than the specks you see dancing in a sunbeam. These tiny particles drifted through the disk, occasionally bumping into one another. Due to electrostatic forces, much like static cling on a dry day, they began to stick together. A tiny grain would attract another, forming fluffy aggregates that grew larger over time. This gentle, incremental growth was the first step in a long journey from dust to planet. This process of small things sticking together to form larger things is called accretion. As these clumps of dust grew, their gravity increased, allowing them to pull in more material. Over thousands of years, the dust bunnies grew into pebble-sized objects, then boulder-sized ones. These larger bodies continued to collide and merge, building up into objects kilometers across. These were the first small worlds, the building blocks of planets. We call these mountain-sized bodies the planetesimals. The disk was now a swarm of these small objects, all orbiting the young sun on similar paths, like cars in a massive multi-lane highway. The journey was not always gentle. Collisions could be destructive, shattering a growing planetesimal back into smaller pieces. But over millions of years, the largest objects continued to grow, their gravitational influence becoming dominant. They swept up the smaller debris in their paths, clearing out their orbits. It was a case of the rich getting richer, as the biggest planetesimals grew fastest, eventually becoming planetary embryos, the size of our moon, even Mars. The disk was becoming less of a dusty haze and more of a system populated by a few large, dominant bodies. These planetary embryos were the seeds of the planets we know today. Their final size and composition depended entirely on where they were in the disk. The story of our solar system is not just one of creation, but also of location. The heat of the sun created a fundamental divide in the disk, sorting the ingredients, setting the stage for two very different families of planets to form. Close to the young sun, the protoplanetary disk was a very hot place. The solar wind, a stream of particles flowing from the sun, was incredibly strong. It blasted away the lighter gases like hydrogen, helium, leaving behind only heavier materials that could withstand the heat. In this inner region, only rock metal could exist in solid form. Therefore, the planetesimals that formed here were dense, rocky bodies. They continued to collide and merge over millions of years, eventually creating the four small, rocky worlds we call the inner planets. Mercury, Venus, Earth, Mars. These terrestrial planets are defined by their solid surfaces. They are worlds you could, in principle, stand on. They are relatively small and dense, composed of an iron core rocky mantle crust. Their proximity to the sun meant they never had the chance to gather the vast amounts of gas that existed farther out in the disk. They are the compact, solid heart of our solar system, each with its own unique history of volcanic activity, impacts atmospheric evolution. Their story is one of formation in a hot, violent environment, where only the toughest materials could survive. Their gravity was so strong that they began to pull in the abundant hydrogen-helium gas directly from the surrounding nebula. This led to the formation of the gas giants, Jupiter, Saturn, and the ice giants, Uranus, Neptune. These outer planets are enormous and have no solid surface. Jupiter and Saturn are composed almost entirely of hydrogen-helium, the same elements that make up the Sun. Uranus and Neptune, forming even farther out, are called ice giants because they contain a higher proportion of water ammonia, methane ices beneath their gaseous atmospheres. The outer solar system is a realm of giants, worlds of swirling clouds, powerful storms deep, crushing pressures, a stark contrast to the small, rocky worlds closer to the sun. As the planets formed, they became miniature systems of their own with their own gravitational influence. Moons, or natural satellites, came to orbit them through several different processes. For the giant outer planets, some of their moons likely formed in a similar way to the planets themselves. As Jupiter and Saturn gathered gas from the solar nebula, they were surrounded by their own smaller disks of material. Within these disks, accretion took place on a smaller scale, building the large, regular moons that orbit these planets in the same direction as their spin, much like a miniature solar system. Another common way for a planet to get a moon is through capture. A passing asteroid Kuiper Belt object might stray too close to a large planet. The planet's powerful gravity can snag the object, pulling it into a stable, though often irregular, orbit. Many of the smaller outer moons of Jupiter and Saturn are thought to be captured bodies. Their orbits are often tilted, highly elliptical, or even backward compared to the planet's rotation. These captured worlds are like cosmic trophies, reminders of the chaotic early days of the solar system when objects were frequently scattered across different orbits. A third, more violent method of moon formation is through a giant impact. The leading theory suggests that about 4.5 billion years ago, when the Earth was still young and molten, it was struck by a Mars-sized object named Theia. The colossal collision vaporized parts of both bodies and threw a tremendous amount of molten rock and debris into orbit around the Earth. Over time, gravity pulled this ring of debris together, which eventually coalesced to form the moon we see in our sky today. This explains why the moon is made of rock similar to Earth's mantle and has a very small iron core. It is a child of the Earth, born from a cataclysmic event that shaped the future of our planet. Phobos Deimos may also be captured asteroids, or perhaps they are remnants of a larger moon that was shattered long ago. Each moon in our solar system tells a unique story about its planet's past and the dynamic history of its cosmic neighborhood. A natural satellite is any celestial body that orbits a planet or a smaller body. The solar system is home to over 200 confirmed moons, and some of them are worlds as complex and fascinating as any planet. Among the most remarkable is Jupiter's moon Ganymede. It is the largest moon in the entire solar system, a giant that is bigger than the planet Mercury. Ganymede is a world of contrasts: dark, ancient, heavily cratered regions, younger, brighter terrains with grooves and ridges. This suggests a dynamic geological history. Data from the Galileo spacecraft strongly suggests Ganymede may harbor a vast ocean of liquid salt water beneath its icy crust. This hidden ocean could contain more water than all of Earth's oceans combined. A moon so far from the sun holding liquid water is astounding. The water is likely kept from freezing by heat from tidal forces, the constant gravitational stretching and squeezing from Jupiter, and by decay of radioactive elements in its rocky core. If there is liquid water, if there is a source of heat, if there are the right chemical ingredients delivered by comets over billions of years, then Ganymede becomes a place to consider the possibility of life. It represents a new paradigm in our search for habitable environments. Saturn's largest moon, Titan, challenges our definition of Earth-like. Titan has a thick, dense atmosphere, even thicker than Earth's. Composed mostly of nitrogen with a small amount of methane, its orange haze hides the surface in visible light. When Cassini and Huygens arrived, they revealed a stunning landscape: weather clouds, wind, rain. On Titan, where the surface is a frigid 179 Aus, the rain is liquid methane. Methane rain carves river channels, pools into vast lakes, and fills great seas near the poles. Titan is the only other place with stable surface liquids. Like Ganymede, Titan likely has a massive subsurface ocean, water mixed with ammonia. A subsurface ocean is liquid water beneath an ice shell warmed by internal heat. These hidden oceans are prime targets in the search for extraterrestrial life. Our understanding of the cosmos is constantly evolving. Each new year brings fresh discoveries that refine our story of the solar system. The year 2025 has been no exception, filled with exciting breakthroughs. One tantalizing idea continues to gain traction: the hypothesis of a distant hidden planet, sometimes called Planet Y. Astronomers have noted that the orbits of some distant objects in the Kuiper Belt are strangely aligned. It's as if they are being shepherded by the gravity of an unseen world. Calculations suggest this could be a small planet, perhaps between the size of Mercury and Earth, lurking in the dark outer reaches of our system. In August 2025, a team using advanced imaging techniques announced the discovery of Wispit 2b, a protoplanet still in the process of forming around its star. At only 5 million years old, it is one of the youngest planets ever directly observed, giving us a rare snapshot of planetary birth in action. Then, in October 2025, another team captured a direct image of HD 114311 ABB, a massive planet orbiting a pair of stars on a roughly 300-year orbit. An exoplanet is any planet that orbits a star outside of our own solar system. Closer to home, a new celestial companion was found. In September 2025, astronomers identified 2025 PN7, a small asteroid known as a quasi-moon. This object doesn't orbit Earth in the traditional sense, but it shares our orbital path around the Sun in a complex, temporary dance. It will remain a loose companion to our planet for the next 60 years or so. These discoveries highlight the ever-changing nature of our cosmic map and the power of new observational technologies to fill in the blanks. Meanwhile, the James Webb Space Telescope continued to deliver breathtaking views of our own planetary neighbors. Its 2025 observations of Jupiter's auroras provided unprecedented detail, showing the intricate interplay between the planet's powerful magnetic field, its volcanic moons, and the solar wind. We also saw the third known interstellar object, 3I Atlas, pass through our system. This object, an interstellar comet, originated from another star system entirely. Such visitors are cosmic messengers, carrying clues about the makeup of planetary systems far beyond our own. An interstellar comet is a comet that has come from the space between stars, rather than from our own solar system. Exoplanet, a planet that is located outside of our solar system, orbiting a different star. Beyond the orbit of Mars lies a vast, sparse ring of debris, a region that separates the inner rocky planets from the outer gas giants. This is the asteroid belt, not a crowded, chaotic sci-fi field. Rather, an enormous expanse where millions of rocky bodies orbit the Sun. Most asteroids are small, from boulder size up to a few hundred kilometers. All that material combined would make an object smaller than the Moon. The asteroid belt is leftover material from the early solar system. Jupiter's immense gravity prevented those planetesimals from forming a planet. So they stayed scattered, a fossil record of the inner planet's building blocks. Studying them reveals the early solar nebula's composition and conditions. The largest object, Ceres, is spherical, a dwarf planet. The belt lies between Mars and Jupiter. Moving much farther out, beyond Neptune, we enter a much larger, icier realm. This is the Kuiper Belt. It's also a ring of leftovers, but with very different inhabitants. In the cold, dark Kuiper Belt, the objects contain rock and frozen ices, water, ammonia, methane. The Kuiper Belt hosts hundreds of thousands of bodies over 100 kilometers across, and an estimated trillion-plus comets. Pluto is the Kuiper Belt's most famous resident. Pluto has its own moons. Pluto has mountains of water ice. Pluto has vast plains of frozen nitrogen. Discoveries of other large objects, Eris Makemake, led astronomers to rethink what a planet is. The Kuiper Belt is a vast, icy frontier, a primordial reservoir untouched for billions of years. These icy bodies are time capsules holding clues to how the outer planets formed and where Earth's water came from. If you travel even farther out, far beyond the Kuiper Belt, you reach the theoretical edge of our solar system. Here lies its largest and most mysterious structure, the Oort cloud. It is not a belt or a disk, but a gigantic, spherical shell of icy objects. It surrounds the Sun, the planets, and the Kuiper Belt at an immense distance. Its inner edge may begin thousands of times farther from the Sun than Earth. Its outer edge could extend almost a light year away, nearly a quarter of the way to Proxima Centauri. The Oort cloud is believed to be the home of long-period comets, those that take thousands or even millions of years to orbit the Sun. We cannot see the Oort cloud directly. Its objects are too small, too dark, and too far away for even our most powerful telescopes to detect. Its existence is inferred from the orbits of comets that occasionally fall into the inner solar system. These comets arrive from all directions at all angles, suggesting a vast spherical shell, not a flat disk like the Kuiper Belt. The objects are primordial relics from the solar system's birth. They likely formed closer to the Sun, in the region of the giant planets. Gravitational interactions in the chaotic early system flung them into distant orbits, especially Jupiter and Neptune. They have been drifting in the deep freeze of interstellar space ever since. Every so often, a gentle gravitational nudge from a passing star, a giant molecular cloud, or the tidal forces of the Milky Way can disturb one of these icy bodies. That disturbance can send an icy body on a long journey inward toward the Sun. As it nears, the sun's heat vaporizes its ices, creating a glowing coma and a long tail. Each comet is a messenger from the most distant, ancient part of our solar system. Our solar system, as we know it, will not last forever. Stars, like people, have a life cycle, and our sun is in its stable middle age. It has been steadily fusing hydrogen into helium in its core for nearly 5 billion years, and it has enough fuel to continue doing so for about another 5 billion. But eventually, the hydrogen in its core will run out. When this happens, the sun will begin a dramatic and final transformation. The core will contract and heat up, causing the sun's outer layers to expand enormously. The sun will swell into a red giant. Its surface will grow so large that it will engulf the orbits of Mercury and Venus. It may even expand far enough to swallow the Earth itself. As it grows, it will become hundreds of times more luminous, but its surface temperature will be cooler, giving it a reddish-orange hue. Even if Earth is not physically consumed by the sun, its fate is sealed. The intense heat from the bloated star will boil away our oceans, strip away our atmosphere, and bake the surface into a molten, lifeless rock. This red giant phase will last for a few 100 million years. After the sun has exhausted its new fuel sources, its outer layers will drift away into space, creating a beautiful, glowing shell of gas known as a planetary nebula. At the center of this expanding cloud will be the sun's dead core, a small, incredibly dense, Earth-sized object called a white dwarf. This stellar remnant will no longer produce new heat through fusion. It will simply be a hot ember, slowly cooling and fading over trillions of years until it becomes a cold, dark, black dwarf. A red giant is a late stage in the life of a star when it runs out of hydrogen fuel in its core and swells to an enormous size. The surviving outer planets will continue to orbit this faint white dwarf. Their orbits may be altered, and some planets could even be ejected from the solar system entirely during the sun's violent final stages. The solar system will become a cold, dark, and silent place, a ghost of its former self. This is the ultimate fate of our cosmic home, a powerful reminder that even on the grandest of scales, everything in the universe is subject to the relentless passage of time and the fundamental laws of physics. The story of the solar system is more than just a sequence of astronomical events. It is our origin story. It connects us to the cosmos in the most intimate way, tracing the journey of matter, a simple cloud of interstellar dust, the complex world beneath our feet. When we study formation of planets, the composition of asteroids, the hidden oceans of distant moons, we are searching for clues about our own beginnings. We are trying to understand the precise set of circumstances that allowed a rocky planet in just the right place to become a cradle for life. This grand narrative is one of constant change and discovery. It teaches us about the immense scales of time and space, fostering a sense of perspective and wonder. The same gravity that pulls an apple to the ground sculpted the planets and holds the galaxies together. The same elements forged in the hearts of long-dead stars make up our bodies. This story shows us that we are not separate from the universe. We are a part of it, a way for the cosmos to know itself. Our story isn't over, it's accelerating. New tools widen our eyes to the cosmos. Each discovery reshapes what we thought we knew. Questions drive us forward. Are we alone? What other worlds are being born right now? Keep exploring with us. Subscribe for more.